Hi, this is a short CERR demo. CERR, as you know, stands for Computational Environment for Radiotherapy Research. It's written in MATLAB, which is widely used for research. CERR is distributed with open source GNU GPL license, so it's free to download and use. CERR has a website, www.cerr.info, which also houses CERR Wiki. CERR is distributed via GitHub. You can clone CERR or just get a zip file dump. So once you also CERR has a Google group called CERR Forum. It has about 10 posts per week, and you can find answers to common questions about, for example, if you want to resize a scan, if you want to use dose calculation or access beamlets, you could look for those keywords in CERR forum and find answers. Now, once you download CERR, you will get folders containing MATLAB.m files. Then you could add those files to MATLAB's path by going to File, Set Path, and say Add with subfolders and select top level CERR directory. I've already added that here, so no need to add again. You can save the path and then go to MATLAB's command window and just type CERR CERR, and a brief control panel will pop up. There are three major options here. Importing data stored in various standard formats like DICOM, RTOG, some native gamma knife, plunk formats, and convert those formats into .mat CERR specific format. Uh, there is another option to export .mat files to DICOM, which could then be read by various other planning or image viewing software. And there is another option to actually look at the RT objects within MATLAB CERR environment by going to a review study and clicking at viewer. Just a short demo of importing DICOM. If you have a folder containing a patient's DICOM, which has various objects like CT, RT dose, structures, treatment plan, then you can say I want to import those things into CERR by going to import, selecting the folder containing DICOM files, and then saying open. This would scan all the DICOM files in this directory and give you a tree which shows various DICOM objects present in that directory. So under here, you'll see there are 4 series. First series is CT modality, second series is RT struct data, which are anatomical structures contoured by physicians. Third series is volumetric RT dose that was delivered or rather planned. And the fourth series is RT plan, which gives you information about beams and beam geometry and monitor units and so on. So you could import, you could say import all here, and CERR will convert all these RT objects into native MATLAB format, which can then be visualized within CERR. So I'm just cancelling out here. Now let's assume that we converted this DICOM to CERR, and we are interested in looking at what we imported. So we go to viewer, and by going to this file menu, file open, you can open the data that has been converted into CERR format. You can go to an example case here. I have a test cohort. Let's look at an example. Okay, so this is how the imported data looks in CERR. So as you see, there is a scan, a CT scan, and there is a radiation therapy dose overlaid on the top of the scan, and there are anatomical structures which are being shown here. There are various options to, there are various viewing options. You can toggle these RT objects on or off. For example, if I toggle dose off, I cannot see dose. I can toggle structures on and off. Can change transparency between scan and dose. I can selectively choose which structures to display and which not by uh, clicking at uh, these structures in from the legend panel, or I can go to the structure drop down and further select which structures to show and which not to show. I can change the layout of various windows uh, from here by going to view panel layout. Let's say I want to have 4 medium, I could do that. Then there is a option to apply zoom to particular view. You can zoom in, zoom out from any of the transverse, sagittal, or coronal views. Then there are various options to display dose as a color wash or isodose representation. So I can toggle that by choosing this, toggle isodose color wash. Now I can see isodose representation of these dose distributions, and then you can further select isodose line options to control which levels of these dose distributions to display. I'm going to toggle it back to color wash. You can toggle the plane locators on and off by choosing view, toggle plane locators. Now you can, there are various options to uh, choose the color bar. You can double click this color bar and you can choose a different color bar for your dose distribution. You can, for example, this hot cold and say apply. Now my dose is shown with a hot cold curve. So the default is star inter. Can also change the color bar range or the dose display range from here, or you can do that by dragging these tiny triangles. What this is doing is this is only showing me dose that is between 0 and 0.572 and just nulling out all dose which is not in this range. Now if you drag this upper triangle down here, this will still show me dose between 0 and 0.866, but dose above 0.64 will all be shown with this red color. So you could play with various dose display options from this color bar. You can change, now let me turn off dose for a second. Now you can change the centering and width for your scan by manually typing in numbers here. Let's say I want to center my image display around Hounsfield units of 50 plus minus 200 by 2. So 200 is the entire width. So this will change change the way scan is displayed. There is also a interactive windowing. Can click here, and you can drag a mouse on any particular view, and uh, dragging from left to right would change the width, and dragging from top to bottom changes the center of this image display. There are also default presets. For example, there are defaults for head, liver, bone, lung, and so on. I'm going to select abdomen default here. So much for various view options. Uh, uh, there are options for dose management by going to dose management. From here, you can get some basic stats about this dose. How big is the dose? How much memory does it consume? Whether you want to delete this dose, or whether you want to store this dose remotely, so as to free up space in your MATLAB memory, and then call this dose as and when required. So you could do all these things by going to dose management. You can add or subtract different dose distributions by going to dose, add, subtract, reassign. Reassign is nothing but you can assign a dose belonging to scan 1 to some other scan. If you want to um, sum or subtract doses, you can enter a name for your newly created dose called sum dose, and you can associate that with scan number 1. Now, if there are multiple scans, they would show up as a list of those scans here. Then you can check the doses that need to be summed up, and you can apply weights. If you apply a negative weight, then that would mean the dose with negative dose weight is going to be subtracted from others. So the dose summation could be done from here. I'm going to turn on my dose. I haven't summed up the dose. I just went to the GUI and then exited out. This is still the original dose which is showing up. Over here you can toggle between various doses. In this case, I have 3 dose distributions, and I can select which one to display from here. There is an option to do a 3D gamma calculation to compare various dose distributions. We will look at with a different plan where I have two doses which are where one is shifted by a particular amount, and that will be a good test of this 3D gamma. So we'll look at that later. There is a IMRT module, stands for intensity modulated radiation therapy, and what CERR lets you do is you can define beam orientations by selecting beams. So over here I selected 3 beams, and I can set angles for those beams by uh, 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 moving them on this GUI. Or I can input the angles, my gantry angles here. Instead of 32, I could say I want it at 50 degrees, and then this would move. Um, Then I can select the um, um, select my target structures. Let's say uh, I will have my target as entire prostate, for example. So this is my target structure. Uh, you can have more than one target. In that case, the union of those structures is used as a target, and the isocenter is nothing but a geometrical centroid of the union of these structures. So when you're here, you could also um, ask CERR to show up how these beams would actually look in all three views, and you could go to you could check these boxes on, and uh, that way you can look at the cross section of beam number one. If I check beam number two on, then I'll see cross section of beam number two, and so on. So once you are satisfied with beam orientation and beam parameters, you can say I want to. You can set a dose calculation algorithm and its parameters, and you can say you can name this dosimetry, and then you can say go, and that would create beamlets for this particular kind of beam arrangement and for these beams. So as an example, let's do a quick dose calculation, but with just one beam to save time. So I'm going to delete these two beams, and over here um, I'm choosing just structure number uh, 11 as my target, as well as a structure to calculate a dose for. I could select skin, and that would give me a dose calculation for entire skin. But in this case, we would get dose only for this prostate. So I can say go. Now this went back and calculated uh, beamlets uh, for this beam. And if I want to show those on CERR Viewer, I could say uh, show, and I can enter beam weights. In this case, I will just leave blank to equally weigh them. Structure number, since we calculated those for structure number 11, we would have to enter structure number 11. Let's name our new dose with, say, IMRT beamlet test, and um, that's all we need to define here. And if we say okay, now this um, went back and calculated those for this particular beam geometry. And this is how the dose looks for the structures we selected. So I'm going to zoom out. I'm going to get out of IMRT module. To exit, I'm going to say yes. Um, Now, this might also be a good time to actually look at where all this metadata uh, and the data which user has generated is stored. So let's go to MATLAB, and everything that all the RT objects within CERR are housed within a variable called plan C, and that can be accessed by declaring it as global from CERR command window. So you could say global plan C. And plan C is a is a cell array where each element of this cell holds a particular type of RT object. For example, element number 3 holds information about scans. Element number 7 might hold information about structures, and so on. And this index mapping is stored uh, within the last element of plan C. So if you could do plan C end, okay, that will give you that tells us that scan information is stored at third index, beams are stored at seventh index, structures are stored as fourth index, and so on. So I can define a variable for this called index s, and anytime I'm interested in accessing a particular RT object, I can type in plan C index s dot scan, and that gives me my scan array, which is 256 by 256 by 30 slices. It gives me other information like how it was uniformized and so on. So uniformization is a step with which the slices that are irregularly spaced are converted into regularly spaced slices so that they can be displayed in sagittal and coronal views. If you want to look at uh, uh, index s dot im, it will give you information about intensity modulated radiation therapy beamlets that we just generated. So we can look at our IM dosimetry, and if you further drill down to beams over here, we see that we have only one beam that we generated, and then you can further get information about uh, the beam parameters and the beamlets that got generated, the x and y uh, geometrical positions of the beamlets, and so on. There are numerous functions that have been written in CERR, or you can call them as utility functions that are used to get data in and out of these RT objects. For example, if you want to get the XYZ physical grid of a scan, you don't have to go and mess around with calculating it yourself. There is a utility function called get scan XYZ vals, and I can just use this function uh, uh, and pass my scan structure this way, and it would give me X vals, Y vals, and Z vals. As you can see from here, they are of size 256 by 256 by 30, which was the size of your scan array. You can look at raw scan array by going to plan C x dot scan dot scan array. Let's say I want to plot the 10th transverse slice. I could just say figure image C, and here I get my transverse slice. You could further use this information in prototyping your segmentation, registration, or any other algorithms. So you have a very programmatic and easy access to the underlying RT objects via CERR and the utility functions that it provides. Going back to our graphical demo, um, now let's look at the metrics drop-down options. Um, so CERR provides various kinds of metrics that are commonly used in radiation therapy. For example, you could calculate dose volume histograms for a particular structure and dose distribution by going to metrics dose volume histogram. Can select a dose to use in this calculation. You can select anatomical structure, and you can add this to the calculation. You can say I want to look at the volume histogram in a cumulative manner, and this gives me uh, the green line is the dose versus fractional volume. You could also select to display absolute volume if you check this or if you toggle this absolute flag on here. There are various other graphical options you can play with by going to expand options, and you can wish to um, you can drag a line here, and that would give you the percentage volume that's above this line. Again, this data is also available uh, in a programmatic fashion by going to plan C s dot dvh, and um, you'll see a dvh matrix stored here. There are also utility functions to get this data out. For example, there is a function called get dvh matrix, and so on. Now there is another kind of histogram uh, uh, which is I think uniquely available in CERR. It's called dose location histogram. Now with dose volume histogram, there is no information regarding the location of these dose voxels, whether they were located deep inside the structure or whether they were located on the surface and so on. So you can get that information from dose location histogram. So in order to generate dose location histogram, you can select a dose distribution. Let's select some. Let's select our favorite prostate structure, um, and it requires a criteria um, for selecting the voxel. So let's cho choose a criteria to find uh, cold spots within prostate. So let's define cold spot as the voxels that have dose less than say 55 grays. And now let's compute DLH. Okay, so this tells us that there there is no uh, voxel that's less than 55 gray. That's why we see zero volume here. Okay, let's define something which is more useful. Let's call, let's say 65 gray. Oops, nothing again. Okay, let's actually see how what the dose distribution looks like to this structure. I'm going to turn off all the structures and just show my prostate, and I'm going to see if there is any. I'm going to set my dose display range to 0 to 70 gray. Okay, so as you can see, everything in this prostate looks like it's above 70 gray. Let's choose 71. Okay, so now you see small portion which is below 71. Okay, let's go back to dose location histogram, and now let's have a criteria of 71 gray for cold spots. Let's compute dose location histogram. Okay, so now we get a curve. Um, what a dose location histogram is showing us is a histogram of um, uh, it's showing us distance versus volume, and it's giving us a histogram of uh, cold spots at a particular distance from the surface of a structure. So you can also get information in text format from this box. From here you can see that there is a total volume of 26 cc, which is cold spot, and from this figure you can see look at you can get the distribution of these cold spots. For example, um, you can see that uh, cold spots of about 19 cc were located about 3 millimeters from the surface of this structure. Changes back to 2.59. There are other kinds of tools here that let you compute standard radiotherapy metrics like Vx, Dx, MoX, MockX, and so on. And you can do a comparison of these metrics between various structures by going to this tool. I'm not going to do an example here, but this is the way to do it. Another neat metric or neat tool in CERR is dose projection. So over here, the structures and doses can be projected along transverse, sagittal, or coronal views uh, for various modes like minimum, maximum, or mean. So you could look at uh, all voxels uh, going down from head to toe in case of transverse projection, and look at a mean, max, or minimum along that direction, and show it here. So for example, let's look at let's calculate the minimum dose for prostate. And let's select our dose set to be the sum. And this is how the projection looks for minimum. So you can also um, go to print mode uh, to change the background to white. You can select crosshairs, and that will display the row, slice, and column coordinates, as well as the actual dose values. And if you are interested in going directly to that slice, you can check this box on, and then you'll go to that slice in CERR Viewer. So this tool is useful in finding hot and cold spots, and looking at a dose distribution in a very compact format. There's another option for intensity volume histograms. It's similar to dose volume histogram that we looked at, but it works on scans rather than dose distributions. So this kind of tool is useful for functional imaging, for example, PET scans, where you might be interested in looking at distribution of SUVs versus the volumes. Uh, there is another tool to apply NTCP modeling and seeing how the NTCP curves change when you change the parameters in your models for particular doses and structures. There's another unique tool in CERR called plan robustness analysis. Now with this tool, um, you could check how robust your treatment plan is for organ motion. So what you could do is select a dose, select the structure for which you want to simulate the organ motion. Then you can select the number of fractions in which this dose was delivered, and you can repeat a number of trials. Let's say you want to do 10 trials and 50 dose fractions. And you can apply systematic and random shifts. Now these shift values could be calculated from previous experiments, looking at IGRT images and those kind of things. So for here, let's assume certain shifts. Let's say 0.5 centimeters, zero point 0.2, zero point 0.2. Let's not have any rotation. Let's provide random shifts, and let's have CERR calculate the histogram curves by taking into account the organ motion. So what CERR is doing is it's applying these specified motions to these organs, and repeatedly calculating dose and these DVH curves. Okay, let's try and apply a bit more motion. So we can actually see a difference. Okay, so yeah. So now I see uh, original curve which is in uh, solid, which is a solid line, and the expected curve which is a dashed line, and I can display the confidence bounds for this histogram. I can display 1 sigma, 2 sigma, 3 sigma bounds, and I can drag a line here and look at the numbers in this text box. Similar to dose manipulation, there are functions for scan manipulation. You can go to scan management under scan and delete a particular scan or save it remotely to disk to save your memory space and so on. There is also option to do image uh, registration and image fusion, which we will look at in a with a different data set. You could look at significant images. So CERR also imports annotations and looking at significant images lets you look at the slices that have annotations marked on them. There are various options to play with anatomical structures. Uh, you can create a surface mesh out of uh, these polygonal slices for these structures. You could create manual contours on various slices by going to structures contouring. Let's look at an example. You can go to structures contouring. Um, you can tell sir I want to create a new structure. Let's name that structure as test. And there are various modes of operation. We want to select the draw mode, which is by default, and or you can now you can just go ahead on a transverse view and use your mouse to click, 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 draw. You can also do this in a continuous fashion. So once you are satisfied with your structure, you can say save. And as you can see, a new structure got selected, got created in which is shown in blue here. Uh, uh, there are various other options under contouring to edit the structure and do a thresholding and so on. Uh, you can also derive a new structure from existing structures. For example, you can do union between structures, you can take intersection, you can expand the structure in 2 dimensions or in 3D fashion. You can fill gaps if the contours are missing on certain slices, then CERR will do a nearest neighbor interpolation for those slices and show you a continuous structure, a continuous volume. So that can be done by going to this structures, derive new structure tool. You can copy a structure that has been drawn on one scan to another scan by going to copy from one scan to another. You can do you can calculate consensus between between delineations coming from different users by going to structures consensus. Again, we will see that in a different with a different data set. And down here there are options to toggle structures on and off. Now there is also a help option. Okay, so this is a CERR command box, and you can type commands to do basic things like if you are interested in looking at the Hounsfield units for this scan, you can type in scan and hit enter, and then use your mouse to um, query scan. So it tells me here, click, drag in axis, and right click to end. And somehow it's not recognizing my mouse click. I think it's some because of this video recording software. Uh, but okay, so the point is you can type in basic commands from this command box. There is another command called which is very useful, called help, and this will pop up a help window, and it has most frequently used um, uh, commands listed. For example, if you want to delete a particular structure, for example, let's delete the structure which we just created, which was structure number 14. So you can go to, you can type in DL space structure followed by structure number in this command window, or you can click here and enter in the structure index, say OK, and now you see the structure which we created, it's gone. So there are numerous options here for doing most frequently used things in CERR. So this was a brief introduction to basic CERR features. Now let's look at more advanced features like calculating gamma and doing image registrations. Now let's look at 3D gamma calculation in CERR. Gamma metric is used to compare two dose distributions. Gamma metric takes into account both the absolute difference between the two doses and the distance you have to move to find a similar dose. Let's fire up CERR and let's open a plan that contains two dose distributions we are interested in comparing. So I have a phantom for which two doses have been calculated. There is one base dose and there is another dose uh, which is moved by 4 voxels. So let's test whether our gamma metric can pick up this shift of 4 voxels. Okay. Before we calculate gamma, uh, let's define structure around the hot dose region. So I'm going to contouring. I'm going to say I want to create a new structure. Let's call it test, and let's quickly draw a couple of slices. So the slice you just saw, that was the isosector used in dose calculation. So let's save this new structure. Okay. Now to calculate gamma, you have to go to dose, gamma 3D, specify a criteria for dose difference and the distance to agreement in millimeters. Let's specify, usually it's 3 centimeter, 3 millimeter. Let's have even stricter criteria, 2 centimeters, 2 millimeters. Let's choose our two doses to compare. You can specify a threshold value. This so this means all doses below 5% of max base dose, all voxels that have dose below the 5% of max base dose will be ignored in gamma calculation. So with these parameters, let's hit calculate. And now you see um, a gamma displayed on these three views. Let's change our panel layout to 4 medium windows. Let's zoom in. So as you can see, the gamma ranges from 0 to 1.5. Uh, if gamma is less than or equal to 1, that means the difference criteria has been satisfied. So all voxels that are shown in red um, uh, have gamma greater than 1, which means they are not, the doses are not alike in those voxels. Over here you can get get some statistics about gamma metric in a particular structure. Let's select the structure which we just created, and you can see that 42% of voxels pass gamma test and 57% don't pass. So this is how gamma is calculated. You can have access to gamma calculation programmatically. It's stored under, let's do a global plan C index as. So the gamma 3D gamma is stored under indexes.dose. It becomes a new dose which is displayed, which is overlaid on scan. So let's access under plan C dot dose. So now you can see that this plan has 3 doses. So the 2 are the ones that we compared, and the third one is the 3D gamma. And you can access the volumetric data by going to plan C indexes.dose, dose index dot dose array. If you look at the size of this dose array, it's the same size as your as the doses that were compared. Next, let's look at image registration, or how do what tools are available in CERR to compare various images. To do that, let's open a base scan. So I have 2 scans that have been registered to each other using a deformable image registration algorithm, and I'm going to um, open both of them here. So I can open more than one scan, or I can merge contents from different plans in CERR by going to File, Merge Plans. And here I'm browsing to my moving scan. If you go to scan, you'll see 2 CT datasets First one is the base scan, and the second one is the moving scan. To do the registration, I used a utility function provided by CERR called register_scans, and that this is further explained on CERR wiki. So you can go to scan image fusion. Over here, so I'm selecting this lock icon. So if I when I do this, I don't accidentally move the moving scan by dragging mouse on any of these views. And select a different color map for my moving image. So so over here you are seeing a base scan with gray color map and moving scan with copper color map overlaid on top of each other. There are other analysis options. You can take a difference between the base and moving images. So when you see a lighter color, that means there is a higher difference here. You can do a blended checkerboard display. You can change the size of these checkerboard. You can do a image mirror. Over here, you're seeing image to the left, which is a moving image, and image to the right is base image in the same region as the moving image, but it's mirrored. So with this, you can pick up differences between the base and the moving images if the mirror doesn't look very symmetric. There is another tool called mirror checkerboard. Over here, it's similar to the mirror you saw in the previous display, but this is done more locally. So the images are, the portions of images are mirrored within each checkerboard and are color coded for a metric which is selected here. So the color coding is based on mutual information or the mean square error between the base and moving image within the checkerboard. So the red color means a higher mean squared or mutual information metric compared to the blue colored. So the red is worse and blue is good actually. And you can change the size of these checkerboards. Then there is a mirror scope. So here you can move the, you can drag the mirror over the region of interest, and you'll see a mirror pattern for that particular region, and you can change the size of this mirror. So these are some of the image analysis options available in CERR. Now let's look at another utility tool which is more geared towards outcomes analysis. Let's say we have a cohort of CERR plans. For example, plans within this test cohort, and we are interested in analyzing DVHS for a particular structure and dose distribution for all these patients. So CERR provides utility functions to extract this metadata from these plans and store it in Excel or MySQL or a native MATLAB format. So, so let's look at how to do that. So the utility function can be called by typing this name in CERR command window, and you can scan the directory containing these CERR plans. So I go to my test cohort, and let's say I want to extract DVHS for rectum and bladder. And let's say I want to extract a dose which is named as sum. Then I say start scan. Now CERR is going through each and every plan in this directory and looking for rectum and bladder and a dose names sum. And now it's done scanning this directory. It's telling us to proceed to the next tab. So let's go to sum doses. Over here, you have an option to add dose distributions and create a new dose. For example, if various fractions are stored under this plan and you want to use the summation of those fractions in your outcomes analysis, then you have an option to select the fractions and create a new dose out of it. You can go through each and every plan and do this step. In this cohort, I already have a sum plan with all fractions, so I don't need to do this step. So I move to next tab, which is match names. Over here, I see the structures that I asked for, which is rectum and bladder, and the list of available structures for this particular plan I'm looking at. And the same for dose distribution. As you can see, I could find a structure named rectum in this plan, but I couldn't find a structure named bladder. So I'm going to manually assign one of the structures from this plan, which I know corresponds to bladder. I can also open this plan in CERR by clicking view this plan if I want to make sure the structures are indeed what I asked for. So I can say view no structure, and I can look at my rectum and bladder here. So I can do this for each and every plan. So over here, I couldn't find a rectum, and it was named as REKTUM, so I'm going to select that. And same with bladder. So this is where you could do the name mapping between what you asked for and what's available in these plans. So once you are done with this, you can go to next tab where you can actually review all these plans in 16 plans at once. I can say I want to look at my rectum structure for these 16 CERR files. And say viewer, CERR is taking data for the rectum from these 16 plans and creating a display for us. Okay, so over here you can see a 4 by 4 grid of the rectum structure and the dose distribution. So this is a good way to QA your data set. You can also change slice and see how it looks on different slice. When I move, all the rectums are moved by a specified physical delta value. So once you are done selecting the structure names and QAing those structures, you can go to a final step of extracting these metrics. You can have user-defined metrics, um, uh, as well as in addition to the standard dose volume histograms that get extracted for these structures and dose distributions. You can export data to various formats like DREES or SPSS, readable Excel sheet, or a MySQL database. Over here, you can select the Excel file containing outcomes information. Now the Excel file should have a column that matches the names of these CERR files. That's the key which is used to match Excel outcomes and clinical data from Excel with the DVH data from CERR files. So I'm going to select this column which tells me CERR file name, and I'm going to select additional metrics. In this case, I just have outcomes, and I'm going to select my outcomes variable, and then I say start export. Before I do start export, I have to specify the file name for my DREES file. So let's call it DREES DVHS outcomes, and let's say start export. Now CERR went into each and every file. It picked out DVH for the structures and those distributions we specified. Then it looked at the corresponding outcomes and clinical data from Excel file, combined those information, and stored it in a native MATLAB readable file. Now if you go back to the file we just created, DREES DVH outcomes, we'll see a variable called ddbs, which is a structure array of length 19 because we had 19 plans. And then we could actually look at the metadata uh, uh, for both treatment planning as well as outcomes and other clinical information within here. And this could then be used for your outcomes and modeling studies. So this is a tool to do metadata extraction from CERR plans.